Okay, let's do a problem where we can calculate out and use our knowledge of Poisson's ratio. So an A36 steel bar is loaded with 80 kilonewtons of force. What is the change of length and the change in dimensions across the cross-section of this bar? So the first thing I want to do is I want to take a look at it and let's calculate out what the stress is. For some reason I'm in red. So the stress in the z direction, because if we look at it, we're pulling along the z direction. And so that's going to be the load in the z direction divided by the cross-sectional area over which that load is acting. So our load in the z direction is 80 kilonewtons, so 80 times 10 to the 3 newtons. We're going to divide that by the area. We want to convert this into meters because we want to use base units, and a newton meter squared is going to be a Pascal, and we're going to be comparing it to properties, so it's easier to do it that way. So 0.1 meters, and then 0.5 meters. So that's our 100 millimeters by 50 millimeters. So if I calculate that out, I will get 16e to the 6 Pascal. So, or 16 megapascal. Now this is important because we're going to use this to calculate out Poisson's ratio and whatnot. But the first thing that I want to do is I want to go to my materials properties section of a book. And the reason that I calculated out stress first was pretty easy because I want to compare it against what its yield stress is. So the yield stress of A36 steel, which is actually, I kind of like A36 because it's easy to remember what the yield stress is in PSI because it's 36,000 PSI, which works out to be about 250 megapascal. So 250 megapascal is much greater than 16. We are in the linear elastic region of this material, so anything that we're going to do is going to be completely fine. Now I can also look up the E of steel while I'm doing this, and it's 200 gigapascal. Okay, so I'm in the linear elastic region, and I do have a stress, so now what I can do is I can calculate out the amount of strain that I have, just using Hooke's law. So strain in the z direction is just going to be stress in the z direction divided by the modulus elasticity of the material. So we got 16 times 10 to the 6 Pascal is our stress. And we're going to divide that by our modulus of elasticity, which is 200 times 10 to the 9th Pascal. And once I calculate this out, it's going to tell me the strain in the z direction is 80 times 10 to the negative 6. We'll just put it as millimeters per millimeter. It's also meters per meter, angstrom per angstrom, doesn't really matter. I just put it in millimeters so that way, as I'm dealing with things, it's just easy to do. And like I said, meter per meter, it's all fine. So across the cross-section, it'll be easier for us to do some calculations. So, what do we do now? Well, let's find out what the elongation of our bar is. So our definition of strain is what? It's the deformation, or the elongation in the z direction, divided by the length in the z direction. I'll just do a little bit of a rearranging because I want to know what the deformation in the z direction is. So that's going to be my initial length times the amount of strain I have. My initial length is 1.5 meters. My amount of strain that I have is 80 times 10 to the negative 6. And I'm going to write in meters per meter here because I want this to all work out. It doesn't matter. I can use millimeter per millimeter. Doesn't matter because it's technically unitless. I just change it to meter to kind of match what I've got here. And so now if I go and I calculate everything out, I bash that into my calculator, I will get 120 times 10 to the negative 6 meters. Now, times 10 to the negative 6 is also micro, so I don't know if I have enough room to... Don't have enough room to put it there, so I'll just put it over here. So 120, 10 to the negative 6 is micrometer. So that amount of force is having us elongate our bar by 120 microns, or 120 times 10 to the negative 6 meters. Okay, now we need to do the lateral direction. We actually need one more piece of information for the lateral direction. We need Poisson's ratio. So when we look up these material properties here, we can also look up what the Poisson's ratio of A36 steel is, and we can look that up and find that that is 0.32, which is a pretty typical steel. Typically, you're going to see them in the 0.3s. Oh, and 1 second, I'm going to add a page. I thought I had enough pages for that, but so we just added a page so we can do the rest of our work here. So now we're going to look at the lateral direction. So we've done the longitudinal direction, because remember, E long is the longitudinal direction. In this case, it'd be EZ because I'm pulling along the Z direction. And so that's going to tell me that my lateral strains have to be the off-axis strains, which will be EX, EY, or epsilon X, epsilon Y. Now, they're going to contract in those lateral directions equally. So the strain is going to be the same, but since the cross-section has different lengths to it, we're going to get a different amount of deformation. So if I take a look at this, and Poisson's ratio is what? It's the negative of the lateral strain over the longitudinal strain. So in our case, it's going to be the negative of the lateral, so strain of the X over strain of Z, or negative strain of Y over strain of Z. Once again, I have to stress, this is just this case, because our longitudinal axis is the Z-axis. That's why it works out like that. So if I rearrange this, the strain in X is going to equal the strain of Y, which is going to be negative Poisson's ratio times, I almost wrote out the longitudinal, but the longitudinal is EZ. So negative 0.32 times our 80 times 10 to the negative 6 meter per meter. And so what we get is negative 25.6 times 10 to the negative 6 meter per meter, or more traditionally, negative 25.6 micrometers per meter. So we're shrinking in those other directions equally. And so now we just go back to our definition of strain. So strain is just simply going to be the deformation in that direction divided by the length in that direction. So I will rearrange these. Deformation in the x direction is going to be the length in the x direction times the strain in the x direction. So what do we have? We have the length in the x direction. In the x direction, we're looking at 100 millimeters, so 0.1 meters. We're going to multiply it by the strain, which is negative 25.6 e to the negative 6 meter per meter. And so once I put all of that together, bash it in my calculator, my x direction dimension is going to shrink by negative 2.56 times 10 to the negative 6 meters, or negative 2.56 microns. So that will be the deformation in the x direction. So in order to get that material to make the things longer, that's where some of it's coming from. We do the same thing with the y direction. In fact, I'll just write right into the deformation of the y is Ly, strain y, and then we just plug in our numbers. So the y direction is 50 millimeters, or 0.05 meters. It's the exact same strain, because with the lateral axis strains, they're going to be constant. So that's negative 25.6 times 10 to the negative 6 meter per meter. And I go and I throw this in my calculator, and I'll get negative 1.28 times 10 to the negative 6 meters, or 1.28 micrometers for my deformation in the y direction. And so that's how we would use Poisson's ratio to calculate out changes in dimensions in the off-axes.